everyone. Good morning. We'll begin in just a minute. Well, it's 10 a.m. So let's begin. Hey, where's my recording? Can I see myself? Oh yeah, I can. There's my face. Okay, well, good morning, everyone. How are we doing today? How are we feeling? All right, Karen and Zip, they're doing good. Give us a thumbs up. Fantastic. Well, so today is our second last proper lecture, by which I mean tutorial. The chapter we're looking at today is 42, and next Friday we'll look at chapter 44 on my textbook, which might be chapter 43 in the new ones. So let me clarify what chapter that is by showing you the course outline. Where am I? Yeah. Chapter 44. So right now I'm going to look at atomic physics. The only thing left is then chapter 44, which, due to time constraints, unfortunately, or well, fortunately, we're just going to go up to the radioactivity section. So don't worry about section on the decay process. But we do need to get up to radioactivity, so we need to go at half-lives. And that'll be it. Friday will be the last official lecture. And if I'm looking at my calendar properly, yeah, we don't have class then next Wednesday, 19th. We do have a last class on Friday, the 21st, which will happen from 12:30 to 3:30. So I have a lot of time to talk about the stuff you want to review. Let me think. A few orders of lecture. I'm still putting the final together, but I'm kind of thinking about sort of the material, and it's probably going to lean a bit more towards the first third of the course. Like I'd say it might be like 50% the last third of the course, maybe 40% the first third, and maybe like 10% of the second third. So 10% of the stuff you've seen in the second midterm. You all did really good in the diffraction questions. So I'm not going to ask any questions to do with the double slit, single slit, or diffraction grading. But you can expect some questions to do with angles of reflection, refraction, and thin film interference. That's definitely going to show up, but no double slit, single slit diffraction grading. The other stuff, I'll talk about it soon, and I'll write it down and announce it. But just so you know what I'm thinking for the final, there's definitely going to be a structure similar to the first midterm, where there'll be like a few, 3 or 4 kind of like short answer conceptual questions, followed by about 10 or so, because you'll have 3 hours, long answer questions, which are similar to what you see in the assignments and the second midterm. And again, once I finalize this, I'll write this down in a message. Also,
sure.
Yes.
You know how for the second midterm you gave us an outline to follow? Is it possible to get something like that for the final as well?
So you mean an outline, you say?
Yeah, on the for the second midterm you had given us the topics that are gonna be on the midterm, the second midterm. I don't know if
Yeah.
you're
Oh, yeah, for sure. Yeah. You'll have something. I'm also I dug up some old assignments from like a few years ago, so I'm gonna put this up online so you have like more questions to practice with.
perfect. Thank you.
So yeah, I'll get that too. What am I thinking? So yeah, some conceptual questions for sure, not too many, but you definitely want to be comfortable with, just like stuff we talked about, like relativity, like length contraction, time dilation, the stuff from the first midterm, like the Doppler effect. How does it happen? When does it happen? And what else? Yeah, I'll put up the solutions for the third assignment today. Also, I'll start correcting that. Sorry, for the fourth assignment, and then I'll put up the extra practice as well. For the final, I think I'm just going to supply you with the formula sheet, and you'll get to see it ahead of time. That way, everyone has the same slate. That's my general policy to give you the formula sheets. It's altogether possible that there'll be questions where you don't necessarily have the answer right in the formula sheet, but some things you're kind of expected to kind of know offhand. Like, for example, if an electron gets accelerated through a potential, you should know that the energy of the electron is the charge times the potential it went through. That stuff will be something that wouldn't be in a formula sheet, but the complicated formulas would be on the sheet for sure. But stuff like, for example, the law of reflection, that's something that wouldn't be in a formula sheet, but Snell's law would be. Okay. Let me think. And also, just so I address it now, I know that chapter 40 and 41 are a bit of a curveball and probably more sort of theoretically heavy than the rest of the course. But what I'm really looking for in terms of chapter 40 is if you're able to kind of work out the math to do stuff like the Compton scattering and the photoelectric effect. Some of the later stuff, like double slit experiment, isn't really something you see a question on. It's more theoretical stuff. So don't worry about that. Again, I'll put this out on an outline, but what I'm basically looking for is, if you recall the tutorial we did in chapter 40, the more mathematical stuff of the chapter is probably what you want to work on for practice. As for chapter 41, same idea. What you've seen in the tutorial with it, like when you find the area under the wave function, that kind of stuff you should be able to do. No calculus, but still you should be able to understand that the area under a wave function tells you the probability of finding the particle in that space. And what am I thinking? Yeah, that's all the announcements I have for now. Yeah, again, if you have any questions, you want to work on or you want to look at, I can do them. You can send me an email about them. If you have any questions you want me to look at next Friday, you can also send them to me. Otherwise, I do want to show you some stuff from chapter 42, because I am going to definitely expect you to know how to find the energy transitions for the hydrogen atom, which is basically what we discussed in this chapter. So without further ado, I'm just going to jump right into it. And I'm sharing my screen, am I? Yes, I am. Great. Okay. So chapter 42, only 3 sections and 1 tutorial for it. I held back on doing any puns with the name board during the lecture, so here's my one and only pun. Anyways, the chapter talks about how atoms get to emit and absorb discrete colors of light as they reach different stable energy states. And originally, these were, found experimentally. These were observed as hydrogen atoms. When you send electricity through them, would emit certain frequencies of light. Some of them visible. And it wouldn't be until quantum mechanics or the Bohr model of the atom that there was an explanation for why these discrete lines were being seen. But still, there was this formula right here where you could actually predict the wavelengths of light emitted by hydrogen when it returns to its second state. And it was fairly accurate with what was being seen in spectroscopy. And there's a more general formula that works for the hydrogen atom that basically tells you what wavelength of light to expect when the atom in a hydrogen, when the electron in the hydrogen transitions from one energy level to another, signified by n, the level number, that you can then determine the wavelength of the photon emitted. So when you jump down a level, like from level 3 to 2, you emit energy. And when you jump up a level, so from 2 to 3 or so on, you have to absorb energy. Normally, electrons can absorb energy from photons and jump up a level, but also other particles can collide with hydrogen and pass some energy onto the atom, ionizing them if the energy is big enough. If you want to ionize a hydrogen atom, you need to give it enough energy for it to overcome, for the electron to overcome its bound to the nucleus. In the ground state, the energy of the hydrogen atom is negative 13 electron volts. So provided that you can give it enough energy worth 13 electron volts or bigger than that, then the electron will be energetic enough to become freed from the proton and leave the atom. So funnily enough, the energies of the hydrogen atom are actually negative. At the ground state, the energy is negative 13. And in the second state, which is, N2, which is the first excited state, the energy is negative 3.4. Then the third state is negative 1.5. And then as you go up in the energy levels, the energy slowly approaches 0. But you can notice that the energy levels are a lot closer together. So the biggest gap between levels is between the ground state and the first excited state. So there's an energy gap of about 13 electron volts. Then there's a gap of about 1.5. Sorry, between the second and third states, there's a gap of about like 2 electron volts of energy. So if you jump from the third to the second, you'll emit a long wavelength. But if you jump from the second to the first, you'll emit a much shorter wavelength because you're emitting more energy. Remember, high energy photon has a short wavelength and high frequency. Low energy photon has a higher wavelength and lower frequency. And if you're wondering what the relationship is between a photon's frequency and wavelength, it's always going to be the same formula. Lambda times the frequency equals C. Yeah, look at my attachment. lambda F is equal to C. If we had to get one equation tattooed from this course, it would probably be this one. So now with this chapter, we have the tools to find what kind of photons are emitted or absorbed when the hydrogen atom transitions from one state to another. And we can also find the energies of each state. So with that in mind, let's do some questions, eh? So electrons are accelerated through a potential difference of 12 volts, and they're bombarding hydrogen atoms. What's the wavelength of the atoms? What wavelength of light will the atoms emit? So it might not be apparent right away, but unless you're told otherwise, you can assume that the hydrogen atoms are at their ground state. So the atoms are at their very first energy level, negative 13.6 electron volts. So you might recall, if you studied this in chemistry, that you have a hydrogen atom, and electrons can actually hit it, and then the electron will just end up bouncing off. Some energy can get transferred into the hydrogen atom, and thus with the energy, the hydrogen atom can end up jumping to a higher level and then jumping back down. So it gets excited because an electron hit it, and then it jumps back down. And when it jumps back down, it radiates light. So unlike a photon hitting a hydrogen atom, where the atom absorbs the photon, the electron bumping into a hydrogen atom is more of like a classic collision. Now you might be thinking, wait a minute, Gabriel, you said that X-rays can hit electrons and collide like two pool balls do. How come you're telling me now that photons can be absorbed by a hydrogen atom when X-rays could scatter off electrons? And that is true. X-rays do scatter off electrons, but when it comes to photons generally interacting with hydrogen atoms, the more likely interaction is that the photons get absorbed by the atom. Now, for electrons, though, running into a hydrogen atom, that interaction is like two pool balls hitting each other. And so the electron that hits the hydrogen gives some energy to the hydrogen. And the question is, how much energy does the electron give to the hydrogen? Well, how much energy does the electron have? Then you can find that by figuring that the electrons have been accelerated through a potential difference of 12 volts. So the energy of a single electron is the potential energy it's been accelerated by times its elementary charge. So that will be 12 volts times the elementary charge of an electron, 1.6 times 10 to the negative 19. I won't expect you to memorize the elementary charge, but you should know that this is how much energy an electron gets after being accelerated through a potential. And then you have you can then get the energy of the electron. And at this point, it's 12 times 1.6 times 10 to the negative 19. So 12 times 1.6 e to negative 19. 12 times e to negative 19. You should get 1.92 times 10 to the negative 18 joules. Okay. So this may not seem like a lot of energy, but remember that the hydrogen atom at the ground state only has negative 13 electron volts of energy. So let's see how much energy electron has in a electron volts. So what was it? 1 electron volt is 1.6 times 10. I always get that mixed up, don't I? 1.6 times 10 to the negative 19 joules is 1 electron volts. I'm just doing a unit multiplier to see the electron's energy in electron volts. So 1.6. This gets me 12 electron volts. Okay. So basically, the electron gets 12 electron volts being accelerated through the potential. We can assume that all this energy goes into the kinetic energy of the electron. So at most, the electron can deliver 12 electron volts of energy into the hydrogen atom. If that's true, and the hydrogen atom is in the ground state, then the energy of the hydrogen atom, being negative 13.6, 12 electron volts being given to it is not enough to ionize it, because the ionization energy is equal to the ground state energy. So if the electron had 14 electron volts or bigger, then that will be enough to ionize the hydrogen. But what it can do, though, it does have enough energy to give to the hydrogen so that the hydrogen can go up an energy level. If you recall from the diagram, as a matter of fact, let's just bring the diagram over. If you recall from the diagram, the bottom state is at negative 16, the second state's at negative 3, and the third state's at negative 1.5. So if you can get 12 electron volts of energy from an electron, you do have enough energy to make it to the second state. However, you don't have enough energy to make it to the third state, so basically, because the difference between these two levels is basically what is it, 13.6 minus 3.4. The difference between these two levels is 10.2, while 13.6 minus 1.5. Well, the difference between these two levels, the third level and the first level, is 12.1. So with only 12 electron volts from the electron, you can only have enough energy for the hydrogen atom to jump up to the second state. So it can only get energized to that level, and then eventually the hydrogen atom is going to fall back to the ground state and emit a photon. So the question is actually asking what wavelength will the atoms emit, and in this case, they'll emit a wavelength equal to the difference in energy between the second and first states, because the hydrogen atom gets excited to the second state, and then when it comes back down to the ground state, it loses energy in the form of a photon. So to find out how much energy, to find out the wavelength that gets produced, you can use the formula with the Rydberg constant. Where NF and NI are the levels you're transitioning from and to. So in this case, we're going from the second level to the first. The Rydberg constant here is, I believe, 1.097 times 10 to the 7. So if you plug it in, just rounding off here, times 10 to the 7, you have 1 minus 1 over 2 squared. And but that should give you this about 8.25 times 10 to the 6. This is not the wavelength, it's 1 over the wavelength, right? So you want to flip that over to get the wavelength, which would be answer inverse would be about 121 nanometers. To give you an idea, a wavelength of 300 nanometers is violet light, so 112 nanometers is ultraviolet light. There we go. Okay. Does this question, like, how does anybody want me to explain something about this question again? Does this question make sense? Maybe give me like a thumbs up or a reaction if we're feeling good so far. If you're not, let me know. I'm gonna explain it again. This question, by the way, was in one of Nima's old assignments. Frankly, I think this is a perfect question to be put on a final exam. So if you can tackle this question and approach it, then you'll be in good shape. Okay. Awesome. Well, if no one has any questions, we'll keep talking. Okay, so a hydrogen atom emits a photon of wavelength 650 nanometers. From what energy state to what lower energy state do the electron jump? So remember that only certain photons can be emitted. So because only certain transitions can occur. So let's find out what energy the photon has, because that's going to tell us the gap between the two levels. To find the energy of the photon, we call the formula for energy of photon, which again, it's a very common one, Planck's constant F, which can be written in terms of C and lambda. -36 joules per second times 3 times 10 to the 8 meters per second. 657.7 nanometers 10 to the -9. Okay, so this should tell us 6.626 e to the -36 times the speed of light divided by 657. 6.66 is equal to 3 times 10 to the -1 joules. So as usual, you're going to want to am I doing that right? So you're gonna probably want to convert that to electron volts, because you can then yeah, I'm sorry, I wrote Planck's constant incorrectly. Hey, I wrote this -36. It should be -34. So this should be the answer should be 3 times 10 to the -19 joules. Okay. So if you convert that to EB, right, 3 times 0, 2 times 10 to the -19 times 1.6 times 10 to the -19 joules is 1 electron volt. That should get you about 1.9 electron volts-ish, roughly. Okay, so a photon that had an energy of about 1.6, 1.9 electron volts was emitted. And again, only discrete values, only discrete energies can be emitted because energy levels only have discrete energy values. If you look back at the diagram though for the energy levels of the electron, right, we note that the gaps between the levels tend to decrease really quickly. So for a gap of about 1.9 electron volts, it must have been a transition from the third state to the second state, because the second state is lower than the third state in energy by about 1.9 electron volts, right? The difference between -1.5 and -3.4 is about -1.9, sorry, 1.9. So clearly the photon must have, the hydrogen atom must have jumped from the third state to the second, releasing that difference in the form of a photon. So that's why the wavelength is what it was, because its energy matched the difference between the two states. So. I'll make note of that. Okay. So this question is asking, of all these wavelengths shown below, what's the longest possible wavelength for a photon to still be energetic enough to ionize the electron? So the photon still needs to have enough energy to excite it from the ground state to freedom. So it needs to be at least 13.6 electron volts or higher. So that means that the minimum ionizing photon has an energy, the energy of the photon, the minimum possible photon can ionize the atom must have an energy of 13.6. So in other words, the photon must at least have 13.6 electron volts of energy. And the question is, well, what wavelength does that correspond to? We recall the formula. So then lambda is equal to hc over E. The only thing is that you'd have to don't forget the units. You will have to either write the hc in electron volts or the energy in joules first to get the wavelength. But if you calculate this properly, you plug everything in, because 13.6 electron volts is about 13.6 times 1.6 e to the negative 19. If you use a Newton multiplier, 13.6 electron volts is about 2.18 times 10 to the negative 18 joules. So if you plug everything in here, you should get about 94 nanometers. So a photon with a wavelength of 94 nanometers has 13.6 electron volts. In other words, any photon with a wavelength shorter than that will have more energy. So if you look at the left here, the longest possible wavelength is whichever one is closest to 94, which would be D.
Sir,
Yeah.
could you like re-explain how you got the longest wavelength possible? Because like this looks like you only got like the shortest wavelength.
Right. So the idea is that if I'm a hydrogen in the ground state, for the electron around the atom to be ionized, to be freed from the atom, the hydrogen needs to absorb at least 13.6 electron volts of energy. Do you agree?
To leave the ground state, right?
To be fully ionized, yeah, from the ground state to be ionized from the ground state, it needs 13.6 electron volts of energy added to the system.
Minimum, yeah.
Yeah. Okay. So suppose that, yeah, there's a photon out there that has exactly that minimum energy, 13.6. And if you observe that photon, then the corresponding wavelength ends up being 94 nanometers. A photon that has 13.6 electron volts of energy has a wavelength of 94 nanometers. Does that make sense?
Yeah.
Okay. Now, if you look at the formula though, it looks like the energy of a photon is inverse with its wavelength. So for higher energy radiation, the wavelength of that radiation gets shorter. So any photon that's more energetic than the minimum ionizing photon has a shorter wavelength than the ionizing photon. You need at least a photon with 13.6 electron volts of energy to ionize. Any photon that has more than that, like 20 electron volts, will have a shorter wavelength than 94 nanometers.
Oh, okay. Okay. I understand now. Thank you.
No worries. Right, that's why, like, if you look at the electromagnetic spectrum, and then you have like X-rays, you see that radio waves have, the longest wavelength. X-rays have the least wavelength, but also X-rays are the most energetic, while radio waves are harmless. And also energy is also proportional to frequency. So that's why radio waves have less frequency, and X-rays, while having the shortest wavelength, have the most frequency. Frequency is directly proportional to energy. The more frequent a wave is, the shorter its wavelength. Okay. What value of wavelengths associated with the Lyman series for n equals 2? So Lyman series are the wavelengths that occur when the hydrogen atom returns to the ground state from any energetic state. So if you want to find the energy, you want to find the wavelength of the atom, you can just use the formula here. Don't forget to flip it at the end. So if you get a huge number, it's probably because you forgot to flip. One minus, it's a second level. So this should give you, I think like 12 or 21.1. Yeah. I feel like, so then lambda is equal to so that's all. It's not too bad, eh? Okay. We have 2 questions left, and that's it. Okay. Oh boy, I don't like the formatting here. It should be 10 to the 6. It's in the first Bohr orbit. determines the Broglie wavelength. So it's implied, it's heavily implied here, but the fact that you're told that it's in the first Bohr orbit, that tells you two things: that it's bound to a hydrogen nucleus, and also the first Bohr orbit, the word first implies that it's in the ground state. So, right, so it's the energy of the whole system is negative 13.6. And also it's orbiting, it's the radius of orbit is the Bohr radius, which is about a constant that you don't have to memorize, but the Bohr radius is about here. It's the fifth. It's 0.05 nanometers. It's a tiny amount. Okay, but we were just asked to find the de Broglie wavelength in this case, which that relates to its momentum. So the de Broglie wavelength, this is from chapter 40. The de Broglie wavelength is the Planck constant times the divided by the momentum of the electron. So you should know. I don't expect you to know the mass of an electron, but it's just a good thing to know if you want to keep doing physics. It's 9.11 times 10 to the negative 31 kilograms. That's something I would just give you if I ask on the final. And then, the speed of the electron, 2.1 times 10 to the 6. And at this point, we just gonna plug and play. So by 9.11 e to the negative 31 divided by 2.1 e to the 6, which is equal to 0.3346 nanometers. To give you an idea, if you're ever curious if you got the de Broglie wavelength right or not, for electrons, the de Broglie wavelength is usually like 1/10 of a nanometer. So it's much shorter than visible light. That's why the electron telescope is so good, because the de Broglie wavelength of electron gives really good resolution. Also, if there's ever a question where like an electron is involved, we've seen questions in both relativity and quantum mechanics with like electrons. So in the final, if there's a question involving an electron, it's going to be very clear and explicitly stated what kind of question it is. Like, it's going to be obvious that, okay, this is a relativity question. Look at the relativity formulas. Or, oh, this is a quantum mechanics question. Don't worry about relativity. Look at quantum mechanics. So in this case, talking about the de Broglie wavelength. So it's not about how fast the electron is moving. It's much about the wave particles of the electron in this case. You don't have to consider relativity and quantum mechanics at the same time. That's something for college level physics, and even then, it's something else entirely. Okay. So last question is, an electron and a hydrogen atom makes a transition from the n=4 to the n=3 energy state, and find the energy of the photon. So you don't have to memorize it, but you should have an idea of what the energy states are, at least the first few. So if I show you the ladder of energy levels for the hydrogen here, you'll note that the gap between the upper levels are really short. So you can expect then the energy of the emitted photon to be, much less than 1 electron volt, or around 1 electron volt. So just remember, the first level is about -13. The second level is 10 electron volts higher. The third level is about 2 higher, and the fourth is like half higher than the third. and so on. Just kind of as a rule of thumb, should have a feel for what the energy should be. So when the question asks about this transition, you know it wouldn't be that much. So right, so the energy of any level, right? What is it? It's the ground state energy times the level number squared. And thus, what is it, 13.6 EV by the n squared. So the energy of the photon is equal to the difference in the levels. So we start off in the fourth level, so we'll have negative 13.6 electron volts divided by 4 squared minus 13.6 electron volts
And
by
so
3 squared. Yeah.
There's a minus. Are we jumping down?
Yes. So this formula looks a bit. I know we're used to having in physics, we're used to having like change in x is final minus initial. And I know now for this situation, we're doing initial minus final. That is due to the convention of the hydrogen having negative energy states. In order for the formula to work out to a positive energy, since a photon is being emitted, for that to work out, the formula is written as the initial state minus the final. Because the fourth, despite all of these being negative energy states, the fourth level has more energy than the third. But then for the formula to work out to a positive energy, since a photon does get emitted, positive energy does come out from the transition, the formula is written as the initial energy to minus the energy of the state you transition to. So that ends up giving you a total, that makes the signs work out in the end. 13.6 divided by 16 plus 13.6 divided by 9 gets you probably like around 0.7. No, 13.6 minus answer equals 0.66 electrovolts. There we go. So, right, you're told your transition from this level, your transition from here to here, and because the third level, is lower energy, you release a photon with an energy of 0.66. So that's why the formula is not written like this, because if you write it like this, you will end up with a negative energy. You will end up with like negative 0.66. So the formula instead is written where the initial is first and the final, so that it works out to positive energies being released when you go down a level. And again, this all has to be done because by convention, the energies of the hydrogen atom are negative. That's why there's this unusual formula. And yeah, that's all. You should be able to, comfortably, given an energy for a photon, you should be able to find its momentum, its frequency, its wavelength, or the other way around. And that's actually all really you have to know for this chapter. Then on Friday, we'll talk about chapter 44. And that will be the last lecture. So that's all the stuff I wanted to show you for today. Does anybody have any questions?
I'm like, could you give us that table, that picture on the exam or no?
Of the levels?
Yeah.
Nope.
No? Okay.
But you can
like, memorize?
easily figure it out because you have this formula for the levels, right? So if you start plugging in n equals 1, 2, 3, 4 to this formula, you will get the levels.
Like we just have to know like the first level that's negative 13.6, and then we could get everything else from there, right?
Yeah, exactly.
Okay.
Same with the Bohr radius. The radius of any state is equal to the Bohr radius times the state number squared. So for example, the third state is just 9 times the Bohr radius. Then that's the orbit. I'm talking about the orbit around the of the electron around the hydrogen atom. Yeah, also, you should be comfortable knowing that, what ionization energy is, the fact that photons, you can only absorb discrete energies of photons to go up certain energy levels, but if you're absorbing something that's above the ionization threshold, then that's fine. But below the threshold, only certain photons can be absorbed to jump between the levels. And yeah, that's pretty much it. If no one has any questions, then we're officially, for once, we are done at the official time, 10:50. So yeah, I'm gonna let you go. Feel free to mail me for questions. Again, the next chapter, I'm only gonna cover sections up to 44. So that's like the relativity and half-life stuff. But I won't do 44.5 and beyond. So nothing to do with like gamma or beta decay. So the decay process and forwards, I will not teach that. We'll just go up to the section where you talk about the decay constant, the activity, the half-life, and Marie Curie. And yeah, that'll be it. That'll be the end of the course. So no one has any questions. Wish you all a good day, and we'll see you on Friday.
Have a good day, sir. Bye.
Oh, thanks, you too. Reminder, Friday is the last official tutorial, but then on the 21st, I'll do a review class from 12:30 to 3:30. Oh, you're welcome, Synergit. I wish you a good day.
Thank you, sir. Have a good day.
All right, well, I'm gonna let you all go. All right, goodbye.